Welcome to Revised Chemistry with Mr. B. Let's get straight on and look at a reversible reaction. I've got some blue copper sulfate powder. This is actually called hydrated copper sulfate because it's copper sulfate attached to water molecules, and I'm going to heat it up with the Bunsen burner, and then we'll come back to that in a few minutes to see what's happened to it. Notice how we've got steam coming out of the mouth of the test tube, and we've also got condensation forming on the cooler part of the test tube. After several minutes of heating the copper sulfate, it's turned white, and we've now got anhydrous copper sulfate, and the word anhydrous means without water. So to recap, we've got the blue hydrated copper sulfate being heated up, and it then changes into anhydrous copper sulfate, which is white, and it also gives off water. That was the steam we saw coming out of the test tube, and also the condensation. However, this is not the end of the story, because this is a reversible reaction. Let's see what happens if we add some water to the anhydrous copper sulfate. We can see by the colour it's changing back into the blue hydrated copper sulfate, and you might be able to hear it sizzling a bit. That's because it's also giving out heat energy. This can actually be used as a chemical test for the presence of water. If you suspect a liquid is water and you start off with some white anhydrous copper sulfate and then add the liquid to it, if it changes blue, that confirms that you've got water. Coming back to our equation, the way we show it's a reversible reaction is we use a special arrow. So we have half an arrow pointing forwards and half an arrow pointing backwards, and that is the reversible reaction sign. And that shows that the products are able to change back into the reactants. And that's what we mean by a reversible reaction. Now, to get the hydrated copper sulfate to turn into the anhydrous copper sulfate, I had to heat it up with the Bunsen burner. So I was putting energy into the reaction. So the forwards reaction is an endothermic reaction. And then when I added the water to turn it back into the hydrated copper sulfate, we heard it sizzling and we could tell it was giving out heat energy. So going in the reverse direction, it was an exothermic reaction. And that's true for reversible reactions in general. If it's endothermic going forwards, it's exothermic going backwards. If it's exothermic going forwards, it's endothermic going backwards. I'm going to show you a second example of a reversible reaction. I've got a desiccator here to keep this paper dry because the paper has been soaked in cobalt chloride. And cobalt chloride, when it's blue, is anhydrous. In other words, it's not attached to water. So we're starting off with blue cobalt chloride paper, and when we put it in water, it goes pink. We've now got hydrated cobalt chloride. So this can also be used as a test for water. If you start off with blue cobalt chloride, it will turn pink. Now, because it's a reversible reaction, if I was to put this back in the desiccator to dry it out and come back in a few days, that cobalt chloride would have gone back to the blue form again. If we look at the equation, we can see the blue anhydrous cobalt chloride reacts with water to turn into the pink hydrated cobalt chloride, but that can also change back into the reactants again, and that's what makes it a reversible reaction. In the final example of a reversible reaction, I'm starting off with this white powder, which is ammonium chloride. And once again, I'm going to heat it up with a Bunsen burner. As it's being heated up, it turns into ammonia and hydrogen chloride. But then as it reaches the cooler part of the test tube, those two recombine to form the ammonium chloride, so it's changing back into ammonium chloride, which we're seeing as white smoke. So this time we're starting off with ammonium chloride, and we can tell from the state symbol it's a solid. That's the white powder that we had. And when we heated it up, it turned into two gases, ammonia and hydrogen chloride. And because we had to heat it up and put energy into the reaction, the forward reaction is endothermic. When it got to the cooler part of the test tube, the reverse reaction happened, and these two then recombined to turn back into the reactant. We've seen how with reversible reactions, once you've made the products, they're able to change back into the reactants again. If you're studying for the higher tier paper, make sure you check out my next video, which is all about Le Chatelier's principle. Thank you for watching.